Okay, so welcome back. Today we are going to start looking at infrared remote controls. And you can see I've got here a very simple infrared remote control that is controlling this group of LED lights. And I know that every tech video on the YouTube has got LEDs, so I'm including LEDs in this video. And what we're going to look at is some of the details of how these things actually work. And in the end, we're going to write our own very short code in the Arduino to decode the information coming from this remote so that we can grab the information on which button was pressed inside the Arduino. And we're going to do it in only like 50 lines of code, whereas if you download a free library, they've got thousands or tens of thousands of lines of code. And we probably don't need all that. Like I've mentioned in other videos, it's really good in the engineering world to understand behind the scenes what's going on, so maybe you can write very efficient code that's easy to debug rather than rely on libraries of code that you really don't understand, and if something goes wrong, you have no clue how to fix it. So what we're going to do is we're going to look at what's going on with this simple infrared remote control, and you can see here I've got on my scope, I've got one burst of data that we receive every time we press a button, and it's got encoded in this burst of data which button was pressed. I'm going to trigger the scope and I press a button and you can see that's the actual data. So we're going to look at the actual data and figure out, this is really very simple ones and zeros. We're going to figure out how to decode that. And you can see what this does. It's got 24 buttons and the different buttons do different things. Like I can turn on white lights. I can turn on different displays. I can turn on just green lights or red lights. Now, what we're going to do is I'm going to dismantle this receiver with the LEDs and figure out what's going on in there. How does it decode data from this remote and figure out in this little plastic case what's going on inside here that you can figure out which button was pressed and what we should do and how we should control the lights. So if you unscrew this, you can see on the top we've got all these LEDs. And inside, we've got these 3 AAA batteries to power it. So I'm going to take those out. And if you look, I've got a little printed circuit board. And right here, you can see there is this little device. And we're not sure what that does, but it looks like it's important, so we're going to make note of that. So I'm going to unscrew this and see what's inside of this. Okay, so I've removed the printed circuit board, and on the other side you can see what we've got. And you can see there's all of the LEDs, and I removed this device that we saw before, and it turns out this is the receiver, the infrared receiver. And I hooked it up and applied 5 volts. We're going to see how it's connected, but I applied 5 volts and I'm monitoring that with my Arduino. But there's other circuitry in here that tells the LEDs what to do. But we're going to right now focus on this receiver module, this little 3-pin module. Take a look and see what it does and see how it works. So here is a data sheet for an IR receiver module for remote control systems. And it's probably similar to the one we've got. I'm not sure it's the exact same one, but it's probably very similar. And it's very important you look through these data sheets to find out what's actually going on. So you can see right away it's a 3-pin device, and the pinning is out, which is the signal that has been decoded, then ground and VS. All right. So different models have different pinouts, but it's all basically you apply 5 volts and ground, and you get your output signal on pin number 1 on the left. And you can see over here the supply voltage is 2.5 volts to 5.5 volts, so that's fine. Okay, so now let's take a look at what's going on behind the scenes with an infrared remote control. Because, as I mentioned before, in the engineering world, it's really, really important that you understand what's going on under the hood rather than do what a lot of people like to do, which is kind of copy and paste somebody else's code or grab a library and you really don't understand what's going on. And you know, if you have to debug it, it becomes very difficult, if not impossible. And maybe, as we're going to find out in this situation, all we need is like maybe 50 lines of code to do what we need to do. And, if we download a library, it might have tens of thousands of lines of code, and we have no clue what's going on, and it's far more than we need. So the way we're going to approach this is from an engineering perspective of knowing what's really going on behind the scenes and figuring out what part of that we need for our application. And maybe it's a very simple thing, and once you understand what's going on, you can, I can write a few lines of code to get that done. So that's how we're going to approach this. Now, if you like any of these videos, I encourage you to hit the like button and subscribe and hit the bell notifications. And most of all, please let others know that we're here so we get some more viewers. Really appreciate it. So, infrared remote control. Here I've got my picture of the one we're using. It's a 24-button infrared remote control. And we're going to look into this and see what's going on so we can figure out how we can decode it. Now, what is infrared? Well, in the engineering world, it's often a really good idea to look at the word and try and figure out what the descriptive word is so you can figure out what's going on. Not always the case. Often in the technology fields, the terminology is really poorly done, but in this case, it could help if you look at the word infrared. What does infrared mean? Well, you know what red means? It's a color. Infra means below. It's below red. Infrared is below red. Now, what does that mean? Well, if you look down here, here is a kind of a chart of the various colors that are visible to the human eye. And we go from blue on the left through green, yellow, orange, and to red on the right. The difference with these colors is the frequency range. So you can view it as kind of a sine wave. The light is emitted like as a sine wave, and the frequency of that sine wave determines what color. So for example, on the blue side, this is a very narrow wavelength. You can see the wavelength here in nanometers is 400, and the frequency is 750. Now that's in terahertz, which is 10 to the 12th hertz. So it's an extremely high frequency waveform. But as you vary that frequency, you are emitting different colors of light. So the highest in the visible range is about 750 terahertz with a wavelength of about 400 nanometers. And that gives you a blue wave. And that's kind of the upper end of frequency that's visible to the human eye. As you lower the frequency, we're getting down 675, 630, 590, with a longer wavelength. We're going from 400 up to 500, 600. You can see the color goes to green, to yellow, and to red. And on the far right is the red, the limit of the red range, which is about 780 nanometers of wavelength and about 380 terahertz. What this is saying is if you get into the range of red light with a wavelength of around over 700 nanometers, it's getting to the point where the human eye can't see it anymore, because this is the visible range, and as you go past that, the human eye can't see a red past about 780 nanometers. An infrared signal is something that is below red, or it is below the visible range of light in the red range. So we're talking about something that is a longer wavelength than about 700 something nanometers. This says 780. So above about 700 nanometers, you won't be able to see the light. The light's still there and being emitted, but you just can't see it with your eye. So infrared means it's below the range of visible red light. This remote control is emitting infrared light. Again, you can't see it. It's outside the range of visible light. Now, some people will say, well, I take my TV remote, which is an infrared remote, and it's got an LED. When I press the button, the LED flashes. That means I can see it. No, that's not what it means. That is a separate LED that is designed to give an indication that it's actually sending a signal, but you can't see the signal that it's sending, okay? So keep that in mind. So what's going on? Now we know that this thing is emitting this long wavelength red light that we can't see. So what else is going on? Well, again, we've got these 24 buttons, and we would assume that each button is going to give a unique burst of information to identify itself. So it's going to tell the receiver, okay, the on button has been pressed, and that's going to have a unique code. So each button is going to have a unique code. So what we're going to do is we're going to look at, let's say I've got a remote control and maybe I've got a project and I want to use 2 or maybe 4 buttons of the remote. I need something that is going to sense those 4 buttons or 6 buttons or however many you need. I need something that's going to be able to decode and sense those individual buttons so that we can say, okay, if this button was pressed, I'll go do one thing. If the other button was pressed, I'll do something else. So now we know that each button is going to emit an infrared signal, and it's going to be a coded infrared signal. It turns out in the case we're going to look at, it emits this infrared light in pulses. And you can see here, I've got some pulses shown on this graph, and you can visualize it as an LED pulsing very, very fast. But the problem is you can't see the light coming off the LED. In this case, it's going at about 38 kilohertz, 38,000 pulses per second of invisible light. So the format of these pulses is going to provide information. So in this case, I've got a bunch of pulses that are happening at 38 kilohertz, and then it goes to 0, and then I get some more pulses. And that's what this thing is doing. It's sending out red light pulses that you can't see, and each group of pulses becomes information for the receiver. So we've got these red pulses going out at a frequency of 38 kilohertz, and somehow we're going to have to decode those. So how are we going to decode those? Well, we saw in our infrared LED lights in the beginning that there's this little device here, a 3-pin device. This is a very interesting device because it does a lot of very cool stuff for us. It senses these bursts of red infrared light that happen at a frequency of 38 kilohertz. It senses those bursts and converts each burst of data into a logical 0 or 1. A 1 being 5 volts and a 0 being 0 volts. So that makes it a lot easier because here you've got these pulses coming at you at 38 kilohertz. It's going to convert these into much lower frequency, around 1 or 2 or 3 kilohertz pulses. And then you can take those pulses, and whether they're 1s or 0s, you can decode them and decide which button was pressed. And like I said, in this case, the pulses are going to be returned through this device as a 0, and the absence of pulses of 38 kilohertz of infrared are going to give you a 1. So very nice little device. You just give it 5 volts and it gives you this translation or decoding of these high frequency pulses into low frequency 1s and 0s that you can deal with. This is the waveform that we saw in the beginning when we pressed one button on the infrared remote. And this is kind of like the signal that you're going to see when a single button is pressed. And you can see there's a lot of 1s and 0s here. And somehow at the end of the day, we're going to have to decode this. Now, this particular waveform for this remote is what's called a NEC code. NEC stands for Nippon Electric Corporation, which is an electronics firm that developed this very popular code for infrareds many years ago. And it's very commonly used. There are many other variations, but we're going to look at this particular one because at the end of the day, it's all doing pretty much the same thing. They just are different formats. And once you understand the basics, you can figure out the format. When you think about it, we've got 24 buttons. So really, we only need, indications of 24 states. So you can see here, we've got a lot of these 1s and 0s. Do we really need all that data? And if we're only using like 2 buttons, maybe we don't need all this data. If you look down here, this is kind of the standard format of this NEC code, and it matches very much what we saw on the scope. We've got this initial 1, which is a 9 milliseconds 5 volt signal, and then it goes 4.5 milliseconds of 0, which you see right here, and then all the data starts. And if you look here, all of these bits are actually defined down here. there are 8 bits which are an address code. There's the second 8 bits are the inverse of that address code. Then there's 8 bits which are a data code, which actually tell you what the button was. And then there's 8 bits which is the inverse of that code. So you can see we've got 8, 16, 24, 32 bits. So this defines 32 bits of data. So what's the address code? Well, the address code is there if you want to send this command to different devices. So we've got 8 bits, which means we can have 256 different devices that can receive this code. Whatever this command is from the remote, you can distribute it to any of 256 devices, which is nice if you need it, but do we need that? You know, if you're only going to have one device or a couple devices that are going to get your codes from your remote control, maybe you don't need all this address data if it's only going to one device. So keep that in mind. We've got some address data and we've got some inverted address data. Maybe we don't need that. And then we've got the data code, which has the actual command. And you can see it's 8 bits, so you can have 256 possible different commands or 256 buttons. And this will tell you which button was pressed of the 256 possibles. And then we've got the inversion of that. Do you need that? Maybe not. So what we're going to do is we're going to look at extracting only these 8 bits that actually tell you what the command is, which button was pressed. So now, again, if you download a library, a pre-made library of thousands and thousands of lines of code for infrared remote controls, it's going to have all kinds of decoding for stuff like this, the address and the different data codes. But maybe you don't need all that. And that's why I encourage you to look behind the hood like we're doing here to see what do you actually need and can you do it yourself? Because what we're going to do is we're going to figure out in about 50 lines of code how to extract and decode the command that was sent so we know which button was pressed. And we don't have to rely on libraries that we have no clue what they're doing, but they're, thousands and thousands of lines of code that we can't possibly debug, and we just have to take it on faith that it's working. All right. Now, this particular format of the code is called pulse distance modulation. And you can see that all of these pulses are about the same width, but the distance between subsequent pulses is varying. So like these are all bunched together, and then suddenly you got 2 that are far apart. They have a different distance, and you can use this distance to decode a 0 or a 1. So for example, if they're very close together, you can say it's a 0, and if they're far apart, you can say it's a 1, or vice versa. Now, that's nice, I guess, but we're kind of familiar with pulse width modulation, not pulse distance, and it might be a little bit easier to decode something with a pulse width. Instead of this being distance between pulses, it would be nice if this was just like a wider positive going pulse. So let's look into that. This waveform is a lot like this waveform, but in fact, this is actually the waveform we got on the scope coming out of this device. Now what I did is I took this and flipped it and inverted it to get this. So 1 minus a pulse distance modulation, you can see if you invert this, here is the wide pulses and here's the narrow pulses. Or if you look from this side, they're all narrow pulses with different distances. So it's up to you to go down the rabbit hole of why they use pulse distance versus pulse width. I prefer the pulse width, and I like that this device is giving us a PWM signal because it's going to be a lot easier to decode. So this actual waveform, you can see is normally high, and then when a burst of data is going to come, it comes low for 9 milliseconds, then goes high for 4.5 milliseconds, and after that, we can determine what the actual data is. So now we know we can decode this by using some mechanism in our Arduino or whatever that detects the width of these pulses and we can assign a 0 or a 1 to it because really it's just the inverse of the pulse distance. Okay, so here I have grabbed the code that gets sent by the infrared transmitter when I press the off button on my remote control. And you can see I'm using the oscilloscope application we developed for the Arduino in the recent series. I encourage you to take a look at. It's an 8-part series that shows you how to develop this software to turn your Arduino into an oscilloscope. And we're using that application to grab the burst of data sent by the infrared transmitter. What I'm going to do is I'm going to store that data as a CSV, and I showed you in the series how to hit this single button and it will save all this data as a CSV. And we're going to bring that into Excel and look at the actual data and look at the pulse widths and everything else and figure out how we can decode it. So here is that data from that burst coming from the infrared receiver, and you can see it matches exactly what we've got here. So it's basically a CSV, and I brought it into Excel, and we've got all these different pulses. So now we can start to analyze this and see what the different pulse widths are and figure out how we can decode this and turn them into ones and zeros. So I'm going to use data from my professional oscilloscope just because I've already done some calculations, but it's the same data you can see. And here I've got the time steps and the values, and here is the data that we received. And what we're going to need to do is figure out what are the widths of these pulses so we can figure out what's a 1, what's a 0, and how are we going to decode these. Well, if you look here, I've figured out based on the data what the zeros and what the ones are. So the 0 pulse width in milliseconds is about half a millisecond. So these zeros, these small pulse widths, are about half a millisecond. And the period is about a little over 1 millisecond. And then for a 1, it's about 1.4 milliseconds pulse width and 2.1 for the period. So we're going to have to determine, is the pulse about 1.4 milliseconds or is it about 0.5 milliseconds? And we can use that to distinguish whether we've got zeros and ones. So let's start thinking about what kind of logic we're going to need in our application to determine what this data is. Well, you can see it's normally at 5 volts. It goes down to 0 volts for, what was it, 9 milliseconds, and a positive 5 for 4.5 milliseconds, and then the data starts. So this drop is going to tell us, hey, data's coming. And then we're going to have to find a way that can measure pulse width. And we talked in our previous series about designing a frequency meter with an Arduino, how you can maybe take the rising edge and use that to start a timer and then end it later on. Unfortunately, that looks at rising edges and then the next rising edge. So we're going to have a rising edge to start it and then a falling edge to stop it. So we're going to have to figure out a way to do timing of these pulses, determine pulse width, which tells us whether it's a 1 or a 0. And the first thing we're going to do is, if we have that, we're going to say, okay, well, I've got this long pulse. Let's ignore the first long pulse. If it's 4.5 milliseconds, we know that's just the warning pulse. So we can ignore that one. And after we see that, once we see that pulse, we can start saving data. So we said before that what we really are going to want is like 8 bits here around the middle of the stream of data. We don't need everything. We don't need all the address data. We just need the 8 bits that define what button was pushed. So how are we going to do that? We're going to have 32 pulses. We can measure each pulse, put the pulse durations into an array of 32 numbers, and then we can go through that array and start parsing it and figuring out what the important information is. So for example, if I have an array of 32 pulse durations, I can go through and logically say, well, I only want pulses 16 through 24 or whatever, which is the actual command data over here, and just ignore the rest of these. I can store them for later, but really all I need is these 8 bits, and I can say, okay, what are these 8 bits? And then I can figure out what a number is based on these zeros and ones in this 8-bit group of data. Okay, so now that we have a good idea of how this all works and what our challenge is going to be in terms of generating an Arduino sketch to decode all this, in the next video we'll jump into developing code on the Arduino to make this happen, so that as we press buttons on the remote, the Arduino feeds to the computer different codes depending on which button was pressed. If you like any of these videos, again, I encourage you to hit the like button, subscribe, hit the bell notifications, and most of all, please let others know that we're here so that we can get some more viewers. Otherwise, take care and have a really good day. Thanks.